Hello guys, in this video I'm gonna solve one very famous question, very famous problem in linear algebra, which is if you have a linear transformation uh, for known for two vectors, how you can deduce the linear transformation for another vector, number three vector. Okay, so basically we have here a vector called v, and we wanted to know the transformation, the linear transformation T of V. Okay, given two linear transformations or the same linear transformation for another two vectors. Okay, so we have here T of 2 and minus 1. It gives us 1 minus 1, 1. And T11 gives us 0, 1, 0. Okay, so we have the transformation. Let's write the transformation in that way. We have a transformation that applies to a vector 2 and minus 1. That's basically belong to R2. And when we apply this transformation to that vector, it gives us another vector 1 minus 1, 1, which is basically clearly belong to R3. Okay, it's a three-dimensional vector. That's why this transformation, as said here in the question, it is from R2 or transform or translate from R2 to R3, from convert, transform two-dimensional vectors that belongs to R2 into three-dimensional vectors that belong to R3. Okay? And we also have T of 1, 1 gives us 0, 1, 0. And what we want to know is T of V. T of minus 1 and 2. V equal to minus 1 and 2. Okay, good. So in the beginning, what is linear transformation? It's a matrix. Matrix multiplication. That's it. Don't confuse yourself. So we have some kind of matrix that we don't know in this question here. Then when we multiply this matrix with vectors belong to R2 or 2 by 1 vectors, it gives us other vectors in three-dimensional vectors, 3 by 1. So we have some matrix called T, for example, we don't know it. When we apply T to vectors or an X vector, for example, that belong to R2, it gives us another vector B. This vector belongs to R3. That's it. But we don't know A. We don't know A. Okay? So how to do that? So we learn in our chapter about linear transformation, a course here, that if a vector is the linear combination of other vectors, then the linear transformation of that vector equal to the linear combination of the other vectors. So if we know that V equal to some constant, for example, A multiplied by V1 plus another constant B multiplied V2, where V and V1 and V2 all vectors, then the linear transformation of V should equal to A, linear transformation of V1 plus B, the linear transformation of V2. And of course, A and B can be any number. It's basically belong to R. But I'm gonna use the variables or the naming of the book. So then the book names it R and S. Okay. So I'm gonna remove A and B and put R and S just to make sure you guys are following me. So we're gonna name A and B. We're gonna name R and S. R and S. What is R? I'm sorry, this is it. What is R and S? R and S both belong to R. Okay, real numbers. Good. Do we have this case here? It should be mentioned in the question. It didn't. The question doesn't mention it, but you should assume Otherwise, you will not be able to solve it, you know. You should assume that V is a linear combination of 2 minus 1 and 1, 1. Okay? You should assume that V, which is basically the minus 1, 2 vector, is a linear combination of V1. Let's assume V1 is 2 minus 1, our first vector here, this guy. And let's assume that V2 is our second vector here, 1 and 1. Again, this, I'm sorry, this is this. So R and this, okay? So, by the way, we know T of V1, it is that vector here, and we know T of V2 is that vector here. So, if we could find the R and the S, then we can find T of V, okay? And clearly, we can find R and S. It's very easy, you know? So, let's write this down again. So, minus 1 and 2 equal to R minus R plus S and S. I just multiplied R in this vector and S in the second vector. Then you can add them up. So 2R plus S minus R plus S. Okay? Good. So we have two equations and two unknowns. We're gonna solve it. It's very simple to solve actually without doing Gaussian transformation, Gaussian elimination, but let's do it with Gaussian elimination just to be like compatible with the course. Okay, so we have this system of equation here. We have the first equation, 2R plus S, 2 plus S. Second equation, minus R plus S, minus 1 and 1. And the constant vector here, it is basically this guy, minus 1 and 2. Let's switch the two rows to make like the pivot equal to 1. And put the row 1 as row 2. We multiply the first row by 2 and add it to the second row, minus 1, 1, and 2. When we do that, let's do it with another color to make it clear for you guys. So when we multiply the first row by 2, this will be minus 2, this will be 2, this will be 4. So minus 2 and 2 will give us 0. 2 and 1 will give us 3. And 4 and minus 1 plus minus 1 will basically be 3 as well. So we have here basically 3s equal to 3. From that, s equal to 1. Okay. Now we go to the first equation. We have minus r plus s equal to 2. So minus r equal to 2 minus s. So we can say that r equal to minus 2 plus s. So r is equal to minus 1. So r equal to minus 1. We found it. We get s and r. So what we should do now is basically find the transformation. We know that T of V equal to T of V1 plus T of V2. Just to make it clear for you, so in the book, when he write a vector, he make it bold letter, okay? Small bold letter. Because here in typing, you can just, I'm sorry, when you write with handwriting, it's very difficult to make like bold and light. So we can just put like this symbol here, which represents vector. Okay, that's it. Okay, so T of V equal to should R plus S. So equal to R, which is minus 1. We're going to multiply by T of V1. T is 1 minus 1, 1. Basically a vector. 1 minus 1, 1. plus S. S is equal to 1, very easy. And what is T of V2? T of V2 is 0, 1, 0. 0, 1, 0. So that will be basically minus 1, 1, minus 1, added to 0, 1, 0. So we're going to have minus 1, we're going to have 2, we're going to have minus 1. And that's actually the answer in the book if you want to check, okay? It will be basically, as I said here, minus 1, 2, and minus 1, okay? That's the first solution, okay? We can have another solution. This is basically specific solution to this V, minus 1 and 2. For any vector that span the space created by 2, minus 1, and 1, 1, there is like a general solution that can be applied in that case and can be applied in other cases, okay? For any other vectors, okay? So let's do that as well. So let's name it here. Solution 2, which is general solution. General solution, I mean for any vector V, let's call it V, belong to the span of V1 and V2 vectors. What is V1 and V2? Basically, again, V1 and V2 is our given, like this guy here. This is V1. This is what we call V1. We call it V1. You can call it whatever, X1, X2, whatever you like. And this is Mr. V2. Okay? So let's assume the general vector, which equal to X and Y. We don't know it. Any X, any Y. In that particular case here, X and Y was minus 1 and 2. This is a special case. Now we are making a general solution for any vector belong to the span of V1 and V2. Okay? So what you're gonna do, basically it is the same solution, but you should just change one step to make it more general. Okay? And that step will be that one here. Okay? Oh, I'm sorry, this one. So let's just remove this one here, this arrow. So this basically step will be more generalized here. Okay. So basically, instead of having minus 1 and 2, I'm gonna put X and Y. Okay. So we're gonna have the same two equations, X and Y here, equal to, and then we can have the same 2R plus S, 2R plus S, and minus R plus S, minus R plus S. Remember, X and Y here can be considered known. So X and Y here are known values. Okay, it can be anything, that span like V1 and V2. So you can consider them known. What is unknown for you is R and S. Okay. So we're gonna solve for R and S in terms of X and Y, assuming that X and Y is known. Okay, that's what I'm gonna do right now. So let's do that. So basically, again, you can have the same Gaussian elimination, very easy. So 2, 1, then X. You will not put like a value here, constant value. Then minus 1, 1, and 1. Okay, so I'm gonna switch again, like what we did exactly. It's the same solution. 2 and 1. Multiply the first row by 2 and add. So the first row will remain the same, no change at all. So this will be 2 after this will be sorry, minus 2. This will be 2. This will be 2, 1. Okay. So we add minus 2 and 2. This will be 0. We add 2 and 1. This will be 3. We add 2y plus x. It will be 2y plus x. no change, because x and y can be any values. So from that here, we can say that 3s equal to 2y plus x. From that, s can be represented in terms of x, y, and y as so. 1/3 2y plus x. Then we find r. So we have from the first equation here, minus r plus s equal to y. From that, minus r plus 1/3 to y plus x equal to y. So from that, you can say that r equal to 1/3 to y plus x minus y. You can multiply by minus. Yes, yes. Okay. Then, yeah, it's long, a little bit long here. So 2/3 y plus 1/3 x minus y. So minus y is can be like minus 3/3y. So let's make it more clear for you. So 2/3 y minus 3/3y, which is 1, plus 1/3x equal to 2/3 minus 3/3. Okay, that will be basically minus 1/3. So minus 1/3 y plus 1/3 x. Take 1/3 as a common factor, x minus y. So at the end here, so this is s. So at the end here, r equal to 1/3 x minus y. Remember again, x, y, can be considered known. So we could now found like a general solution for any transformation of any vector belonging to the span of the space of v1 and v2. So basically, t of x and y, t of v, okay, and v here is general, equal to 1/3 x minus y multiplied by, let's make it more even, so t of v1. Okay, good, that's fine. Plus f, s is 1/3 again to y plus x multiplied by t of v2. Okay, and what is that? This is basically t of v. So t of v equal to 1/3 x minus y. And what is tv1? It is basically, we have it here. We should 1 minus 1, 1. 1 minus 1, 1. Plus 1/3 to y plus x. What is t of v2? It is basically 0, 1, 0. So let's multiply 1/3 x minus y with the vector here. So this will be x. Yeah, let's make it more like x alone and y alone to make it more clear for us. So x over 3 minus y over 3, which is 1/3 x minus y. That's it. Here minus x over 3 plus y over 3. Then x over 3 minus y over 3. Why I'm doing that? Because the book is like, the book solved it in that way, which is like, it's more general, of course. We should give credit to the book for that, but it's a little bit confusing, okay? Because nobody explain, you just read this. Plus, that's more easier because 0 will be remain 0, but now we're gonna multiply 1 by this factor here. So 2/3 y plus 1/3 x, and finally again 0. So t of v equal to, then you guys have two vectors, this vector and this vector. You can just add them together. So we're gonna add this guy here to 0, so it will remain the same, x over 3 minus y over 3. We're gonna add this one here to that one here. So let's do this. So we're gonna add the x's with the x, y with the y. So the x minus x over 3 plus x over 3. This will cancel out. Then we have y over 3 plus 2y over 3. 1/3 y plus 2/3 y. 3/3 y, it's 1. So that will be y. 1y. Then x over 3 minus y over 3 plus 0, it will be the same. So x over 3 minus y over 3. Okay? That's basically the solution of the book. If you looked at the book, the solution of the book, you're gonna find it in that way. That's more general. Now let's compensate for x and y with the given values. These values, -1 and 2. Okay? So let's put x equal to -1. Let's put y equal to 2. Okay? That's special case. So T of v in that case, let's see, -1 over 3 minus 2 over 3. This will be 2 x over 3. So -1 over 3 again, minus 2 over 3 equal to, what is that one here? -1/3 minus 2/3 minus 3/3, which is -1. 2 will be 2 again, -1. Let's check. It should be exactly the same. Is it? It is exactly the same. Okay, guys, that's basically it. You have two solutions. One is so specific for like one vector from the span of v1 and v2, and another general solution that can, whenever you know that this vector is like a combination of v1 and v2, that's it. This is the solution. Here you have it. Okay. One final note in that question, although we solved it in two ways now, is that I really don't like the phrasing of the question, because he should mention, the book should mention that, for example, in that case here, that -1 and 2 spans the space created by 2 minus 1 and 1 1. Okay, but I'm gonna prove this for you. So we should to say that v equal to r v1 plus s v2. That means that v belongs to the span of the space that created by v1 and v2. Okay, but let's see that. Let's see if that holds. Okay, if that holds, that means that v1 and v2 are bases of some space in which v is located. So v belongs to some space. Okay, let's call it R2, which is basically R2 because it's two-dimensional vector. Okay, and that means when we say that v equal to r v1 plus s v2, that means that v1 and v2 are bases of R2. Okay, and that means v1 vector and v2 vectors are independent. Okay, so we started our solution assuming that v1 v2 are independent, v1 v2 spans R2, and v1 belong to that space. It is belong to that space, but we should be sure that v1 and v2 are bases, and they are actually bases. Let's prove that. So for any basis vectors, if we say a constant v1 plus b another constant multiplied by v2, this should equal to 0. I'm sorry, if we say that a v1 plus b v2 equal to 0, that means this has only one solution, in which a equal to b equal to 0. Okay, the only solution. So to make v1 and v2 are independent and the basis of R2, then the solution for AV1 plus V2, ABV2 equal to 0 should be one solution in which A equal to B equal to 0. Let's prove that. So A, and we have here V1. Let's, what is V1? V1 is basically 2 minus 1, I believe. 2 minus 1, yes. Plus B, and the other one, I think it's 1, 1. 1, 1, yes. Equal to 0 vector. We should find out that the only solution for that equation basically to hold is when A and B are equal to 0 at the same time. Okay? So if we write the two equations here, we have 2A plus B equal to 0. We have minus A plus B equal to 0. Okay? So we have our Gaussian elimination here. The 2, 1, 0, minus 1, 1, and 0. Let's flip again. So we're going to flip the rows, switch the rows, minus 1, 1, 0, 2, 1, 0. Multiply the first row by 2 and add. This will be 2, this will be 2, this will be still 0. So when we do that, minus 1, 1, 0 will remain the same, the first row, but the second row will be here, will be 0, 2, minus 2, I'm sorry, minus 2 plus 2 equal to 0. 2 plus 1 will be 3, 0 plus 0 is equal to 0. What does that mean here? That 3b equal to 0. That means that b has to be equal to 0 to make the system consistent. Okay? Once b equal to 0, so minus a plus 0 equal to 0, from that a is equal to 0. Then that proves. So V1 and V2 are independent. And the basis for R2 space. And indeed, V, our vector, which is minus 1 and 2, I believe, minus 1 and 2, spans R2, so it's equal to basically some constant R, V1, plus another constant is V2. But, you know, in the exam or when you solve this question, don't do this step. Always assume that the given vectors are the unknown like transformation, the vector for the unknown transformation, in that case here, V, which is minus 1 and 2, is basically constant multiplied by V1 plus another constant multiplied by V2. That's it, guys. Thank you very much for watching and see you in another video. Bye-bye.